Hi everyone, I'm John Poprosky and welcome to my webinar on how to create a perfect VCSEL optical transmitter with driver model. Please type any questions into chat. As I proceed with this webinar, I'll have a questions and answer session at the end of the webinar. You can also email me with your comments and questions at johnb@serdesdesign.com. So, why is this webinar needed? Well, high-speed digital integrated circuits and serializer deserializer systems have their physical layer modeled and simulated in a channel simulator. Channel simulators are designed to use IBIS-AMI models that are based on the IBIS specification. Many commercial IBIS-AMI model generation tools cost tens of thousands of dollars to lease or to own. Today, the SerDes channel simulation technology has matured so that's available for free using cloud-based tools at SerDesDesign.com. Included with the SerDesDesign.com tools are options to generate IBIS-AMI models from circuit data collected from SPICE circuit simulations and hardware measurements. This webinar is to let you know about the process I have used for many years to create perfect models for an optical VCSEL transmitter with driver from circuit data. I created SerDesDesign.com to enable me to create and deliver IBIS-AMI models to 40+ high-speed digital integrated circuit companies over the past 10+ years. Over that time, I learned many processes that practically guarantee a better, more efficient, and automatic IBIS-AMI model building process using free tools. I learned how to create high-quality, low-cost IBIS-AMI models while avoiding the standard approach using high-cost tools. So, along the way, I learned that expensive tools kill all chances you have of achieving low-cost, high-quality IBIS-AMI models. My tools are based on free tools, Microsoft Visual Studio, CMake, web browsers, HTML, and more. I learned that creating an IBIS-AMI model should be the last thing you concern yourself with when it comes to creating IBIS-AMI models. Focus on collecting the correct SPICE circuit simulation data or hardware measurement data, and use automation. My tools rely on automation to generate models from measured and simulated data. I learned how to escape the costly commercial tool trap that keeps most persons stuck in a permanent high-cost model creation situation. Many of my tools are available for free on the web at SerDesDesign.com with options to download and install local copies on your Windows PC. I am here to share my learnings over the past 10+ years and introduce you to the same IBIS-AMI model generation capability I have used to create and deliver high-quality, low-cost IBIS-AMI models. What this webinar will show you. This webinar first gives an overview of modeling SerDes systems in a channel simulator. Then I introduce the process I use to create a perfect optical VCSEL transmitter with driver model. VCSEL stands for Vertical Cavity Surface Emitting Laser and is commonly used in Ethernet and in short-reach applications. Perfect means that the model for the VCSEL with driver agrees with the measured optical output waveform, including the VCSEL effects for different rise and fall waveform characteristics and different current drive levels. Finally, I show you how you can use your data in an electrical repeater IBIS-AMI model and use it in my free channel simulator or any channel simulator. Modeling a SerDes system with a repeater in a channel simulator. Channel simulators are based on the Open Forum IBIS standard, currently at revision 7.2. This figure shows a typical SerDes system block diagram for a SerDes system with repeater between two channels to be simulated using a channel simulator. The block diagram is generic for any channel simulator, but each tool has a specific way to represent this block diagram. The constituent parts of this SerDes system include the following for each channel. The TX IBIS-AMI portions, where the AMI portion typically contains a transmit equalizer, often in the form of a feed-forward equalizer. The IBIS portion provides a differential output to the channel. There's the actual channel which can include a transmit package, the channel characteristics, and the RX package. These pieces represent the differential channel. Each part is optional and may be represented using S parameter files. And there's the receiver IBIS-AMI portions. The AMI portion typically contains a receiver continuous time equalizer, a clock and data recovery unit, and a decision feedback equalizer. The IBIS portion has a differential input from the channel. So a key channel simulator property to keep in mind is that it considers that the entire analog content, the green area in the figure, the total channel, between the transmit AMI portion and the receive AMI portion is linear and time invariant. As an LTI system, the entire differential analog section in the SerDes system is accurately represented by its single-ended impulse response. This key concept enables the channel simulator to achieve its fast simulation speeds. So creating a perfect VCSEL optical transmitter with driver model. This is done from behavioral data that was built into the SerDesDesign.com channel simulator from the beginning. I have used this process over the past 10 plus years, providing custom IBIS-AMI models to over 40 plus companies based on the circuit data they provided me. In today's webinar, I provide instructions on modeling an optical VCSEL transmitter with driver. The modeling data is collected typically from hardware measurements using an optical oscilloscope as well as with a SPICE circuit simulator. This discussion is for a VCSEL transmitter with driver as used in an electrical-optical electrical repeater. This webinar is based on work I did for Reflex Photonics and published in the DesignCon 2021 proceedings titled Proposal for Automated Electrical-Optical Electrical IBIS-AMI Modeling. To start, let's talk about a typical optical link using an EOE repeater. This figure shows a typical optical link system. Inside the ASIC SerDes, there is a transmit and receive, equalization, and clock and data recovery. Inside the optical module, the input current signal drives the VCSEL to emit photons. Photons propagate along the optical fiber. Photons are converted into photocurrent in the pin diode receiver, and a transimpedance amplifier converts the current into output voltage. There are many companies creating EOE repeaters and systems, all contribute towards meeting the needs for the ever-increasing data speeds for data communication centers. Here's an example EOE repeater from Reflex Photonics Lightable system. Reflex is a division of Smith's Interconnect, and there's a link below shown here. This example Reflex Photonics EOE system features up to 300 gigabits of full duplex 12-lane 25 gigabits transmit and receive, or 600 gigabits at half duplex 24 channel at 25 gigabits per second transmit or receive. Bandwidth data communication and can be used with FPGA front-end processing boards. Here's a typical block diagram for an EOE retimer used within a SerDes system. This figure shows such a typical block diagram, and the receiver electrical section includes a differential channel input buffer, input channel equalizer, an AGC, signal detector for signal regeneration, and a VCSEL driver. The optical section includes the optical transmitter with VCSEL, the optical fiber and optical receiver with pin diode detector. The transmit electrical section includes the TIA with automatic gain control, nonlinearity, and output channel equalizer and differential channel output buffer. So modeling the VCSEL module. The key process in modeling the EOE retimer is to model the VCSEL module. The VCSEL module combines the VCSEL driver, which takes a voltage input and provides a current output, and the VCSEL itself, which takes the current input and outputs the optical output power. The VCSEL is typically driven with a defined average current level with the modulating peak-to-peak current level that switches between high and low states. This figure shows the relationship between drive current and optical power output for a VCSEL, which can be quite nonlinear as shown. This shows that the VCSEL emitted power begins above a threshold current, has a peak power, and has a linear current to optical conversion efficiency. The operating point, I average, is typically in the linear region. This figure does not adequately represent the VCSEL characteristic. The VCSEL is very nonlinear and has different characteristics for its rising waveform and falling waveforms. This figure shows the more detailed VCSEL module characteristics as measured by Reflex Photonics. Using a Reflex Photonics Lightable EOE retimer, time domain waveforms for the VCSEL module output optical power were collected for various average current levels with various modulating peak-to-peak current levels. The bit rate of 10.3125 gigabits per second was used with repeating NRZ data patterns of 10 zeros and 10 ones. The Keysight N1090A scope was used with waveform averaging set to 256. The data collected from the scope includes the noise level detected in the waveform. Observe the typical VCSEL nonlinearity with the different rising and falling waveform patterns as the I-mod level is changed. Each rising and falling transient has a duration over several UIs. The VCSEL output has a noise level that is larger relative to the modulation level when the I-mod level is lower. The highest signal-to-noise ratio occurs when the I-mod is larger. There are many possible approaches for modeling the VCSEL module. In the industry, I list some of them here. There's the simple nonlinear model based only on the optical output power versus drive current, as I showed earlier. There's the Keysight physics-based VCSEL model introduced in 2014. There's the VPI photonics software for modeling photonic systems. And there's the Keysight electrical system design workflow, which integrates the VPI optical link. The SerDes.com approach for modeling the VCSEL module is different. It's to treat the VCSEL as, with its driver, as a black box with stimulus response waveforms used to define its characteristic. The VCSEL module was based on the data collected by the optical scope with typical characteristics shown earlier. The measured VCSEL characteristics were provided by Reflex Photonics. With this approach, the VCSEL model is set up as a time-varying filter. The input data includes sets of characteristics for various I average and I mod levels. The model performs a multidimensional interpolation on the data to derive the characteristics for any specified I mod and I average level used. The model is time varying and changes for every simulation time increment. Nonetheless, the model is very fast. The VCSEL model based on measured VCSEL characteristics inherently gives an exact match to the modeling data. There are additional features in the VCSEL module model from SerDesDesign.com, and some are listed here. The VCSEL module model resamples its data for any new symbol rate or samples per symbol used during channel simulation. The module model can apply additional AWGN noise, such as the noise level reported by the scope during the measurement data gathering. The module model can include driver current peaking with one or more peaking steps to compensate for the ISI in the rising and falling waveforms independently. This peaking compensation can be automatically optimized by the model. The VCSEL model can remove its output common mode level for easier use with a channel simulator, which ignores any common mode levels. The common mode compensation can be optimally set by the model, which can be different for different VCSEL settings and data patterns. Here's a discussion on the VCSEL current compensation technique. It's a process used that's based on a process reported in the industry by C. Yang et al. In 2014, listed below. The This figure shows the for a test case with I average equals 6.9 milliamps and I mod equals 5.0 milliamps, the VCSEL model used a 5-step compensation to automatically determine the optimal compensating driver current pulses for the rising and falling waveform responses. These rising and falling current waveforms are overlaid on the optical output power waveforms in this figure using a repeating waveform of 10 ones and 10 zeros. The optical power axis is on the left, the normalized current axis is on the right. The rising and falling currents are normalized to the modulation current level. The optical output power has an average power bias and a nominal peak-to-peak modulation power level. The optimized rising edge has a current piece pulse width of 0.58 UI and 5 compensation peaking ratio. The optimized falling edge has a current peaking pulse width of 0.67 UI and its 5 compensating peaking ratios. This figure shows the VCSEL output power waveform without and with peaking compensation using a repeating waveform of 8 ones and 8 zeros. As can be seen, the peaking compensation corrects the distortions in the VCSEL rising and falling waveforms. The eye diagrams shown here as well shows the peaking compensation for the VCSEL module, and the resultant VCSEL output eye has suppressed jitter and the eye opening height is also near perfect. So here's a summary. This webinar has shown you how to achieve a perfect VCSEL optical transmitter with driver model in an IBIS-AMI model for SerDes channels based on measured hardware data, where perfect means that the model for the VCSEL with driver agrees with the measured optical output waveform, including VCSEL effects for different rise and fall waveform characteristics at different current drive levels. This VCSEL model can be used in the free SerDesDesign.com channel simulator, which is a web-based channel simulators for repeaters, including EOE type repeaters. During this webinar, the discussion was focused on modeling of the laser VCSEL and its driver as used in an EOE SerDes system. This is the typical block diagram shown earlier for an EOE retimer in a SerDes system that is fully configurable in the free web-based SerDesDesign.com channel simulator. This free web-based tool includes IBIS-AMI model generation for the receive and transmit sides of the repeater. This free web-based channel simulator includes its support for repeaters and EOE repeaters and has many free features that were not discussed in this webinar. There are many built-in transmit and receive behavioral models that were not discussed. Many of these behavioral models were used to create custom IBIS-AMI models for over 40 plus customers in the past. This free tool supports the laser VCSEL and VCSEL driver discussed in this webinar, along with optical cables and optical PIN and TIA receivers. So, I'd like to introduce you to your personal Windows PC copy of my SerDesDesign.com channel simulator supporting repeaters, including EOE repeaters. It's the same as the free copy on the web. Your personal copy is a premium account and has many benefits. Without the premium account, the user can only use the same cloud-based tool and CPU that all other concurrent users use, which results in slow performance and lack of direct access to any of your user files. With your own PC copy, your user data and designs are with the privacy of your Windows PC. It does not require internet connection, and it has the speed of your PC. Here's what you get. With the SerDesDesign.com channel simulator for your Windows PC with support for repeaters, it's the same as the repeater tool on the web. It's the same as the electrical optical repeater tool on the web. It includes instructions and examples and features not available on the web, faster simulations using your PC computation power, access to your dedicated user area and files on your PC. It includes an option for generating IBIS-AMI models from the transmit and receive behavioral models you use in your system. So check it out on my dime. There are I personally guarantee that you will be successful using my channel simulator. You have a full 30 days to put it to the test. After that time, if you see value in it, then you can buy it. I only want you as a customer if you're 100% happy with your investment. Simple as that. The SerDesDesign.com premium tools come with a node lock time-based license. You use it free for 1 month, and then after that time you can decide to purchase a 12-month license. See the ordering instructions for your free copy of available tools at this website posted here and posted below this webinar presentation. Well, this ends the presentation content of this webinar. I'll end the recording of the webinar and spend time with you to address your comments and questions. Remember, you can also email me with your comments and questions at johnb@SerDesDesign.com. So, bye for now, and I'm ending the webinar. Thank you.